When people hear passive filters, they think of bunch of capacitors and inductors like on photo, but it's not only used in electronics. It's also in high power applications, and I will show you how do they perform. So let's go to easy schematic, and here we got let's say it's modeled medium voltage. Here we've got transformer to its single phase, but for this purposes I think single phase is just enough. And here we got on low voltage side we've got a low voltage bar, let's say it's a switchgear, and it's feeding here we got load, but it's fed through rectifier or a single phase. Here we got pure resistance load. Here we got resistance and inductive load. Let's say it's some motor, and that's it. And if we check how does it perform, you see that the current flowing here is not sinusoidal. The distortion is because of this rectifier, and the phasing is because of inductive load. So if we for now let's think about this filter as a black box, but if we turn this on, we've got pretty much sinusoidal wave. And let's check the harmonics. Here we got 1.9 kiloamperes amplitude of first harmonic, 50 hertz, and the harmonics are about 60 amperes, 80 amperes, 100 amperes, etc. But without this, this is passive filter. Without this, let's check this. Let's check this harmonics, and as you can see, they are much higher. It's like over 500 amperes. It's like 500 258 amperes, etc. So what do we got here? Let's go to some theory. The voltage on impedance consisting of resistor, capacitor, and inductor, let's say in vectors. So the UL goes up and UC goes down. They are antiphased, and the real the voltage on resistor is here. But if, let's imagine, if the resistance is very low and the voltage on capacitor is exactly the same as voltage on inductor, then we've got almost zero voltage drop here, and it's like a short circuit. So how do we make it? How do we make these voltages the same values? I'll go to some calculations, and it's just easy calculating sheet. So here the capacitor reactance is 1 divided by omega c, and the reactance of inductor is omega multiplied by the reactance, by the inductance, sorry. And if this one equals this one, we've got resonance. So omega is the pulsation, and it's 2 times p times frequency f. And let's imagine we've got 10 millihenries. So the capacitance is, after calculations, needs to be about 20 microfarads for frequency of 350 Hertz. And if we change it for, let's say, 150, the parameters change. Okay, and let's go back to this. Let's go back to schematic. And here. Okay, let's connect it. Let's play. And why does this compensate all of those harmonics? Because each of those branches is short circuit for a certain harmonic. This one is for third, this one is for fifth, seventh, etc. And depending on the rectifier, if we've got a single phase rectifier, we've got third and fifth harmonic. But if it's a 3-phase 6-pulse rectifier, we've got 7th, 9th, and 5th, 7th, 11, 13. It's a natural number multiplied by number of pulses plus minus 1. Okay, and here we can check the current flowing into, let's say, it was third, fifth, seventh harmonic. So the current in this branch should be 350 Hertz. I'll add this. Current flowing through this branch, through this inductance 6. And here on this oscillogram, we can see that the frequency is much higher than the base sinusoidal wave. Can make fast Fourier transformate. Go linear, and as I said, well, it's there is almost always the base harmonic, the first one, but it's okay. And here we've got 150 amperes amplitude of 350 Hertz, as you can see. So it's pretty much most of the current of 7th harmonic just goes through here to the ground. And why do we use them? Because the first thing is they compensate the harmonics. If they do so, the quality of energy is better. There is less heating through all of these components and grid, and there is less distortion for some sensitive devices. And the second thing, because here we've got some capacities, those capacitors can compensate this reactance in the grid, and this I don't know if you can see it, but the current and the voltage is more or less in phase, which is good for network. And we can check it. I'll delete this branch and this branch, and I show you without this filtering. As you can see, the current and the voltage are phased, and the higher cosinus phi there is, the better. So we need to compensate those things. Okay, thank you for watching.